Okay, hope you guys had a good weekend. So we're going to start a new unit today on optimization, focusing on gradient descent type methods. So let's talk about our motivation. So we saw in the last unit that in order to do logistic regression, we had to solve sort of a challenging optimization problem, one that we could not solve in closed form with equations. And just to remind ourselves what it was, we wanted to find the minimizing vector W of this cost that was the cross entropy loss. So we had natural log of 1 plus e to the power zi minus yi zi for zi equal to the inner product between our features, test features, and we append a 1 for the bias term. And over here we have our W vector, and I'm doing something a little bit different than the last unit. So in the last unit we had B as the intercept, and we had coefficients W1 through WD. But now, to keep the notation a little bit simpler in this unit, we're just going to put B as W0 and basically not have any B. So that way, this W vector starts counting at W0, goes all the way up to WD. That way we don't have to talk about B and W separately. Okay, so this is the problem we want to solve for logistic regression. And we know that this can be done with scikit-learn. And we would like to know a little bit more what's happening in scikit-learn when they solve this problem. What actually are they doing to minimize this? Because that's a really important concept in machine learning, is how you minimize loss functions. So basically that's the high-level goal for this unit. So we have to start just talking about some kind of basic things first. Things we've talked about before, but we're going to revisit them again. So let's talk about gradients. So, so the sort of generic problem that we encounter in this unit is we want to minimize some cost J over some coefficients W. So J is just going to be, it could be this function that we saw up here, or it could be something else. So we're just being generic. So there's a cost J. And let's think about the gradient. So one important thing about the gradient that we learned way back in Unit 2 was that the place where the gradient goes to 0 is the minimizer, at least one minimizer of this function. So if we can find the W that makes the gradient go to 0, we know we're at the solution, and that's kind of what we've used until now. But something else that we'll dive into a little bit more today is that, let's say we're not at the optimum solution. So let's say we're somewhere over here. So this is, by the way, this is the minimum in this picture. If we're over here and we want to find that minimum, if we can't solve for the gradient zeroing solution, maybe what we could do is we could move in that direction. And we could keep moving in that direction iteratively. And so something special about the gradient that we'll prove in a moment is that it gives the direction of maximum increase and the slope. So in other words, to go to the solution, we need to go in the negative gradient direction. Here is the maximum in this little toy example. This is the minimum. And these are the equal cost contours. And those little blue arrows show you the direction of the gradient as well as the norm of the gradient. That is, the longer the arrow, the larger the norm of the gradient. So in other words, the steeper the cost function at that point. And then something to keep in mind is that not all functions have gradients. Not all functions are differentiable. So we're going to focus on functions that are differentiable for most of this unit. But if we have a function that's not differentiable, then a lot of the things we talk about here can't be directly done. And something we'll talk about a little bit later today is gradients can also be used to linearly approximate a function, which will be very important for us. Okay, so let's start at the beginning. How do we define a gradient? So if the parameter that we're trying to optimize, W, is a vector, then the way the gradient is defined is the partial derivatives with respect to each of the vector's components. So we would have actually, okay. So this would be in the case that this is a d-dimensional vector. So here, the gradient is a vector of the same dimension as W. And the first element is just the partial derivative with respect to the first term in W. The second element of the gradient is partial derivative of the second element in W, and so on. Okay, so that's the familiar case we've been working with. But we also know that sometimes we want to optimize over matrices. Like when we did multinomial logistic regression, W is actually a whole matrix. The different columns in W would be like the binary predictors for the different classes. So we want to optimize that entire W matrix. So in that case, the gradient takes a different form. The gradient is also a matrix, but the partial derivatives are just the corresponding elements of W. So in the top left corner, we have the partial derivative of J with respect to W11, which is the top left element of W. And then as you go across the columns, you have the partial derivative with respect to dW1K. So this is if this has K columns. And again, if this has D rows, then as you're coming down this way, you get DJ, W, D, W, D1. And in the bottom left-hand corner, you have the partial derivative with respect to the dth row and kth column of the W matrix. Okay, so in this case, you have an entire matrix. And later when we get into neural networks, we'll go beyond matrices. We'll actually have tensors, which are like multidimensional arrays. And the gradient in that case is exactly the same shape as W always. And we just, we do the same thing. We just take partial derivatives of the cost with respect to each element of that tensor, that multidimensional array. So the idea is whatever shape W is, the gradient has exactly the same shape. And it's just defined element-wise by the partial derivative with respect to the different terms in the thing we're trying to optimize. Yes?
So what are the rows and columns representing here?
So as an example, we said if we're doing multinomial logistic regression, then every column would be the K versus not K binary classifier. And every row corresponds to the jth feature in our data set. Right? So if we had binary classification, then we would have this, but if we have more than two classes, we would have this. Okay. All right, any questions on how the gradient is defined? Okay, great. So let's do some quick examples. So here, we're starting out real simple. We have W, it's just a vector of two parameters. We have a cost function written with respect to those parameters. And we need to compute some partial derivatives. So let me ask, is Ling Hao Tian here? No. Okay, what about Clayton Moeller?
Right.
All right. So how do we do this first one?
It would just be W2 cubed, right?
Uh,
Oh, wait, no,
Right.
just 2 W2 cubed.
exactly. And then let me ask, is, let's see, Evan Menges here?
Yep.
What about the next one?
6W1 W2 squared.
Right, okay. Yeah, so we'll be doing a lot of these like partial derivatives in this unit. So yes, that's what we have. So now that we've computed the individual terms, we can just stack them into the gradient. Like this. And an example of doing this in code is on the right. So here we have a function where it's called jeval, and it returns two things. It returns both the cost, j, as well as the gradient of the cost with respect to the parameters w. And as you can see, what it does first computes the cost, then computes each term of the gradient exactly as we did here, and then just stacks them into a NumPy array. And then later, to see this in action, we sort of arbitrarily make a vector w with elements 2 and 4. We evaluate this, returns j and the gradient, and we print them, and this is what we happen to get. At that location, the cost and the gradient are those quantities. Okay, and this is also a NumPy array, the thing that it returns. Okay, so that's just sort of a toy example. Here's another example that looks a little bit more similar to what we will see in this course, where we have some sort of cost that is a sum over some training samples indexed by I. And then here's the cost, and if you look closely, this is essentially what you would do if you wanted to fit an exponential model to data. Yi are your targets, xi are your features. An exponential model would scale xi, exponentiate it, and then scale that. So there's two tunable parameters, a and b, and we would like to find the a and b that best relate our features to our targets with this exponential model. So here we have slightly more complicated partial derivatives. Let's see, is Bethany's here? Yeah. So what do you have for the first one? How do we approach this?
First, we just take derivative square, so then,
Okay, so yeah, what happens to the sum? Does the sum stay?
no.
Okay, well, let's look closely. So we have sum over the different i's, right? So when we take this partial derivative, we know that by linearity, we can move it through the sum. And then we'll actually take the partial derivative of this with respect to a. But we will have something for every single I. So the sum will stay. So let's write the sum there. Okay, so we'll have, so then we need to take the partial derivative of this, and so how do we do that?
First, you do derivative of it as a whole, like 2 times y minus.
Exactly, 2 times this times the derivative of this with respect to a. So the 2 will cancel the 1/2. So we'll just have the sum, and then we'll have yi minus a e minus b xi, and then we need to take the partial derivative of this with respect to a. So that's just going to be this part without the a. So it's going to be another term here, minus e minus b xi, like that. Okay, and then we can do the other one. Is pretty similar. It's a little bit more complicated just in the very last term. The first term is the same. For the last term, we need to take the partial derivative of this with respect to b. And when we have an exponential, so we're going to get minus a e minus b xi, and then we take the partial of what's in the exponent, which is going to be minus xi. So let's see. So we're going to have an xi here, and then cancel the minus there. Okay, so it's a bit more complicated, but something we can do. And then we stack these two things together, and we get our gradient. And now we build another function to evaluate this. So I want to point out something that's important about Python, is it gives you some shortcuts that allow you to apply scalar operations to matrices, vectors, tensors, things like that. And that's called Python broadcasting. So let me give you an example. If I had two vectors, let's say, I don't know, if I have x is x1, x2, and y is y1, y2, we know that x times y doesn't exist, right? Because it doesn't satisfy the rules of matrix multiplication or vector multiplication. But if you, in Python or NumPy, if you just do x, let's see, this doesn't exist. But NumPy allows x times y, which is interpreted not as a matrix multiplication, but as a scalar operation, where it will take the first element in x, multiplied by the first element in y, store that as the first element in the output, and then take the second one times the second one, multiply those, store that in the output. And that is called Python broadcasting. It's just one example of how you can apply scalar operations to vectors and matrices in ways that are kind of illegal from the perspective of matrix algebra, but if you understand that these are scalar operations, you just need to interpret them differently. So we can see that happening several places. Okay, let's look at this line. So here we see that, x is going to be a whole vector of terms across our different n samples. And so b is a scalar, but b times x is another vector. And here we're exponentiating a vector. That's illegal. There's no such thing as an exponential of a vector. There is such thing as an exponential of a matrix if that matrix is symmetric and square and so on. But yet we can do this in NumPy because it's actually doing something different than exponentiating a vector. It's actually exponentiating every term in that vector. Okay, so I just want to be clear about what's happening here. So if you write on an exam e to the x, you'll get points off because that doesn't exist. But you can program that in Python and it actually has a different meaning. It's basically e to the x1, e to the x2, and so on. So these are different ideas, right? But that's what NumPy broadcasting is. And so we'll start to see a lot of this when we look at the Python code in this unit of many examples of scalar operations on vectors and matrices. Here's another one. So we see y air. This is another vector because y starts out as a vector. C is a vector. We can subtract and we get a vector, but now we're squaring a vector, right? So what we're actually doing is squaring each term in that vector, element-wise, and then summing across it. Okay, so any questions on Python broadcasting at a high level? Okay, so we'll see some examples, more sophisticated ones as we go through the notes. And this is a link. And if you click on that link, you go to some really nice documentation on how exactly everything works and all the tricks you can do with NumPy and broadcasting. Okay, any questions so far? Excellent. Okay, so now we're going to get into a little bit more math. And we're going to talk about approximations, first order approximations. And we're going to start in the simplest case where we have right now a scalar input function. So what that means is I have a function j of a scalar w. So w is just a scalar number, j is just a function of that. So as we know from previous, calculus classes, is that we can do a Taylor series as a way of describing any function. And so the Taylor series in this case would look like, and so this is the Taylor series of this function at the point W naught. Looks like this. We have J evaluated at that reference point W naught. And then we're going to have the gradient of J evaluated at W naught times the deviation between W and W naught. So here W is the term on the left, and this W naught is this reference point. So that's the first couple terms, and then we have another term, like actually it's going to be 1/2 dj, or d squared j W naught dw squared W minus W naught squared. And there's going to be an infinite series of these. There's going to be a cubic term and a quartic term and fifth power and sixth power all the way to infinity, right? But for our purposes, we don't really need all that detail. So what we're going to do is we're going to say that all these terms beyond the first can be summarized using a notation that's called big O notation. And this big O is going to be big O of the deviation from the reference squared. Okay, so we got to talk about what is this big O stuff. So how many of you guys have heard of big O notation? Okay, glad that a few of you have. If you haven't, it's not a problem. The idea is that when you say, like, just informally, when you say big O of epsilon squared, where epsilon is intended to be a small number, it means that there's some upper bound that is at most a constant times epsilon squared. So here we're saying all this stuff, all this infinite stuff, all together, we can upper bound it by a function that's quadratic in this deviation between W and W naught. And we don't know the constant. There is some constant, we don't know it, but we know there is some constant out there. That's essentially what it means. And the nice thing about this is it kind of tells you a summary of all this complicated stuff. It just summarizes it in its most important form for now, which is to say we have a constant term, a linear term in this, plus this quadratic term with some scaling. And even though there's all this other stuff, at the end of the day, we can just think about this as quadratic through this bound. If you want more formal definition, if a function g of epsilon is big O of epsilon squared, it means that there exists two positive constants, c and epsilon, such that g of epsilon is less than c times epsilon squared for all epsilon between minus delta and delta. So that's what you would get if you take a course on real analysis, which is something a lot of grad students take. So that's when you learn about these, you see these over and over and over again until your head hurts. But basically that's the formal definition of this. And in many cases, like even though we don't know the constant, we can derive something where the constant doesn't actually matter. And we'll see this happening several times. So the way that we're going to typically use this is an exact equality. J of W is this entire series, or it's the first terms plus this extra term. But when we want to approximate it, maybe we just keep the first two terms. So this is an approximation. Notice we're going to use the approximate equal sign. And now we're just going to write the first two terms alone. And this approximation is certainly not perfect because we're ignoring this big O term. But at the same time, we know exactly how perfect it is. The deviation between the truth and our approximation is exactly this big O term, which means that it's no worse than a quadratic as those terms W and W naught get close together. And here is a picture of it. So the blue is the true function J of W, plotted versus W. And here is our reference point W naught. And this is this approximation here. So you can see the approximation is linear because when you look at this equation, you can see it just changes linearly in W. You have W times some constant. That gives you the slope. And then these other two terms give you the intercept, which happens to be down here. So overall, you're saying, I have this complicated function. I'm going to approximate it as linear at this point. If I'm exactly at that point, I have a perfect approximation. As I start to deviate from this point, I know that my approximation error is quadratic. So if I'm very close to my reference, I should have very small error because I would have a small number squared, which is even smaller. But as I start to get away from my reference, you can see approximation error can get really big. Okay, so this is going to be useful when we are near the reference. When we're far from the reference, it's not really useful. But often, we care about what happens when we're near the reference, and then this could be a good enough approximation. So that's essentially how we're thinking about it. We have basically a slope and an intercept, and that's our approximation of this maybe very complicated function. Okay, so this is a good time to pause. So what questions do you guys have on this? Is this sort of making sense? A lot of ideas here. This is kind of key. This provides the intuition, and then we're going to move forward and we're going to do this for vectors, and we're going to do it for matrices. So, but the intuition is sort of the same. It's just that the notation starts to get more complicated. Yes?
You mentioned quadratic
Where's the quadratic?
Yeah.
The quadratic is sort of here. So we have a constant term, constant in W. We have a term that's linear in W. And we're saying that all these other terms together, which all this stuff is not necessarily quadratic, but we can upper bound it by some quadratic. So this is saying like all this extra stuff is no greater than some quadratic function here. This is the quadratic. So I don't know, maybe on this plot, like maybe maybe the blue function could be very wiggly. So you could see like there's very high order terms. But essentially we're saying that there's some sort of quadratic bound that where all that wiggly stuff is just, we're basically condensing it all and saying it's within that big O. And that way we don't have to worry about all the details. We just know that this is no bigger than a quadratic with some constant C. So this is the bound. We don't know what that constant is, but we know that there is some constant out there. So we'll see some examples in a couple slides. Okay. Any other questions for now? Okay. Okay. So let's repeat this for functions. Vectors. So now we have a vector input functions. So that means J takes in a vector, and we'll say this vector is W1 through WD. So now we have to fix a reference point. Again, we'll call it W0, but this W0 is a vector. So if we look inside, we would have like W01, W02, all the way to W0D. So we would like, again, to do a first-order Taylor series approximation. And so it has a similar form, just a tiny bit different. We're going to have J evaluate the reference, where, again, the reference is now a vector. And now we're going to have a sum of gradient terms, J equals 1 to D. And this is the partial derivative of J evaluated W0 with respect to the jth entry of W. And now we're going to multiply it by a scalar Wj minus the reference W0J. And so you can see that this is very similar to what we had on the previous page, except now we have a sum of partial derivatives, whereas in the previous page we just had a single kind of plain derivative because there was only one parameter. So that's really what's changed. And we're going to have a big O term, and now the big O is going to say it's quadratic in no more than the squared norm between this W, and our reference. So there's a lot of, crazy terms in this Taylor series, but we're basically just summarizing them all in this big O term. It just makes it a lot easier to interpret. Hides a lot of the unnecessary detail in here. Okay, so is this extension kind of clear? It's really doing the same thing from the previous page, but it's doing it sum over each component. Okay, so now let's just rewrite it a little bit differently. So here we have dj, dwj. So you might remember that this is the gradient, but looking at the jth term of the gradient, that's what this is. And then this thing here, this is like the vector difference between w and the reference, but looking at the jth term. And so basically this sum is like sum of the jth term of one vector times the jth term of another vector. But that should be familiar to you. You can write that as the first vector transpose times the second. So that gives you something of this form, right? First times first plus second times second plus third times third and so on. So in other words, this is actually the gradient vector transpose times this difference. And so far, we've been keeping the big O term, but at some point, we're going to make our approximation. And we're going to do that just by dropping the big O term. We're going to say this is a good approximation as long as W is close to the reference, meaning this norm is small. Because then this term, which is sort of the approximation error, that is small. Okay. Is everybody good with how we went from here to here? Okay. And now one last thing is inner products. So we've talked about inner products before. And in this course, we've sort of talked about the inner product for vectors. And the idea is if you have two vectors, you transpose one, multiply by the other, and we call that the inner product. So basically that's this. And that's true. That is the inner product. But it's really just one kind of inner product you can have. It turns out that in linear algebra, you can handle very generic objects that are very different than lists of numbers like this. You can handle functions. You can handle matrices. Those things can all be handled similarly, and you can then extend the notion of inner product to those things too. You can have an inner product between two functions. So what does that mean then? How can we interpret an inner product? So the basic intuition for an inner product is that it's a way of measuring angle between two objects. Those objects could be vectors, like we're dealing with here. They could be functions, they could be matrices. And when you define that inner product, you can basically interpret it this way, no matter what you're dealing with. You'll have essentially the norm, or the length of the first, then the norm of the second, and then the cosine of the angle between A and B. So when we're talking about vectors in some d-dimensional space, maybe these are my two vectors, what I can do is even though I'm in maybe 10-dimensional space, I can look for the two-dimensional plane that contains those two vectors. And now that they're sitting in this two-dimensional plane, I've sort of reduced the problem to 2 dimensions, and I can now just look in that 2 dimensions, the angle theta between them. And that's what we mean by this inner product. Of course, it is also normalized or scaled by the lengths of the vectors too. But that's sort of the intuition behind inner products. So it's kind of cool. Like if I give you two functions and I say, what's the angle between the functions? Well, if you know how the norms are defined, you know how the inner product is defined, you know what the angle is between two functions. It's sort of a nice way of understanding things. Okay, so basically, all we're saying in this last step is that we can think about it as one vector times the other, or we can think about it as this more generic operation as an inner product between two things, which has this notion of angle between two things. And that's a very general notion. And what we'll do on the next page is we'll see that holds true even if we're dealing with matrices. Okay. But for now, are there any questions on anything we've done here, or any questions about this inner product? All right, so let's go. Oh, so we're going to actually pause and we're going to do one thing before we go into matrices. We're going to understand the gradient a little bit, and we're going to get a chance to use our big O stuff. So, okay. So one of the things that I said a few pages ago about the gradient is that it tells us both the direction of maximum increase of the function as well as the slope. So this is sort of a picture by what I mean. So we have this is now, we're working in, maybe we can think about this as like x1, x2, and this is the function on this page. We're calling it j. Sorry, I should name these not x1 and x2, but w1 and w2. Okay, and this is j of the w vector, which includes those two terms. And so if my w vector is right here, this is the origin, and I want to know the gradient of the function at that point, so if I go up, that's the height of the function at that point. That would be j of omega naught, so maybe this is omega naught, the reference point. And if I want to know, like, okay, actually, I said it wrong before, so, okay, so yeah, so we're at this point, w naught. This is the height of the function at that point. And now I want to know which direction do I need to travel here to go maximum uphill for that function. And according to this picture, the steepest point uphill would be moving in this direction and the w plane. And so now that's going to take us steepest uphill. And so we might want to know, first of all, how do we know that the gradient is actually pointing us in the steepest direction? And how do we know what the slope is? How do we know that the slope, how that slope relates to the gradient? So that's what we want to derive for now. So we're going to look at this notion of, sort of a simple notion of what the gradient is. It's actually called the directional derivative. It basically says, like, if I have this function and I move a tiny bit, so epsilon is a really small real number, positive. If I move a tiny bit in the u direction, and I'm going to scale this u vector to be a norm 1 vector, so it's just a direction vector. It just tells me some direction. Well, then the definition of this directional derivative is how far have I moved vertically? Right? I've moved in this, I've moved in the direction u here by epsilon. And this is what we could say the rise over the run. I've moved a total of epsilon here, and this is how much my function has changed, right? So this is basically going to give me the slope here as epsilon goes to 0. Okay, so given this, we can use some of the machinery we've developed until now. So let's start by writing the Taylor series. So if you think about the Taylor series, W naught is the reference. This thing will be like W. This is the perturbed point. So if you look at how far is W from the reference, that's just going to be E times U. So here's how the Taylor series looks. So we're going to have gradient of J evaluated at the reference. And that's going to be inner product with W naught plus epsilon U. This is W minus W naught. Okay, so that, and then okay, there's going to be one more term plus the big O term. And now it's going to be on this. This is like the W minus W naught, but you can see that those terms cancel, and so the big O is just going to be evaluated on epsilon times mu squared. So that's the numerator of this fraction. The denominator is just epsilon. Okay, so So now that you've had a chance to write things down, let me just explain one more time. So if we look at the Taylor series of this term, we're going to have the constant term, j omega naught, but that is going to be immediately subtracted by this, so I didn't include it on the right. And then we're going to have the slope term of this Taylor series, which is this. It's the gradient at the reference transpose times this deviation. And finally, we're going to have the big O term of the Taylor expansion, which is here. So that's how this numerator became this. Is everybody okay with this expression here? Okay. So, all right, so let's look at what happens as epsilon goes to 0. So we have okay, so we're going to have these terms cancel. And when you look over here, this epsilon, you can pull it out if you want here, and that's going to cancel with this one. And that is going to leave you with the term gradient j omega naught transpose times u. Okay, so because these canceled, epsilon's canceled, and all you have left is gradient transpose u. Okay, then the question is, what about the big O term? What about this term? So remember that this term is less than or equal to C times epsilon times U squared. What happens, can we pull this epsilon out of the norm? What happens when we do that? Squares, right? Because we have the squared here. So this is C times epsilon squared times the norm of U. But the norm of U, we said, is just 1. So really, this is C times epsilon squared. At least this term here is upper bounded by C times epsilon squared for some C that we don't know. Okay, but notice that this epsilon, one of them is going to be canceled by the denominator. So we're going to have, in total for this, C times epsilon for some C that we don't know. But when we look at epsilon going to 0, no matter what C is, as long as it's not infinite, that term is going to vanish. So that's gone. And this is all we have. Okay, is everybody good on how we got here? Okay, and now let's write this in a slightly more complicated way. So let's write this with the norm of the gradient at omega naught times this fraction of the gradient transpose U divided by the norm of the gradient times the norm of U. Okay, so why is this true? Well, as you can see, these two terms will cancel, so they go away. And the norm of U is 1, so we can ignore that or leave it in, and then what we have left is the equality we want. Okay, so why did I write it this way? Well, there's something you guys have seen many times before, probably, is Cauchy-Schwarz, which says that when you have this inner product divided by these two norms, the result is somewhere between 1 and minus 1. So that means that this thing here is some number between 1 and minus 1. And actually, you can see that from the previous page, too. If you look at this expression, you can see Cauchy-Schwarz again. If I divide both sides of this by norm of A, norm of B, then this is the cosine theta term, which we know is between 1 and minus 1. Okay, so the point is that this directional derivative, which is basically how, what the slope is at this point, you can see it's the norm times some number between 1 and minus 1. So that means that the biggest this could be, biggest the slope could be, is the gradient. And it's true whenever this term becomes 1, which is exactly when our search direction is in line with the gradient. This is part of Cauchy-Schwarz. It says that this is within 1 minus 1, and that it equals 1 when the two vectors are collinear, pointing in the same direction. They don't have to be scaled the same, they just have to be pointing in the same direction. So this says that as long as u is pointing in the gradient direction, that is the steepest we can get. And number 2, that steepness is the norm of the gradient. So that's a proof. The gradient tells us the direction of maximum increase and the slope. Okay, so this is the maximum slope. It occurs in this direction. Okay, so this is just done to give us some intuition and to see how we can use some of our Taylor series linear approximations. It's not the last time we'll use them. We'll use them for some important algorithm design stuff. But here we see them in action. All right, so there's a lot going on this page. Any questions on anything at all? Anything with this part? Okay, so here, hopefully you can see some uses for our Taylor series linear approximation, as well as interpretation of the gradient. Okay, so this is for vectors. Now let's do this again for matrices. So maybe we're doing multinomial logistic regression with 3 or more classes. Then we have a vector of parameters we're trying to design. And so we have some cost function or cross entropy loss, or something else, whatever J is. And we'd like to do the same thing as we did before, Taylor series approximation. So we're going to take J at the reference matrix, W naught, but now we're going to have 2 different sums, some across the rows and some across the columns. So we have partial derivative with respect to the ith row, jth column of W. And here we have the deviation between that scalar value and the reference point. And there's a lot of other terms in the Taylor series, but we don't care about them. All we care about is that we can think of them together as upper bounded by this big O term. And in this case, the big O term is the Frobenius norm squared between that error. And if you remember, the Frobenius norm of a matrix is just, or squared Frobenius norm is just the sum of all the terms squared. So it's a direct generalization of what we saw with vectors, where we also had all the terms squared and summed. Okay, so this is, again, very similar to what we saw before, but now we just have sum of all the scalar gradients, which are actually, as we see here, these are the different terms of the gradient, right? This is just the ith row, jth column of the gradient matrix, or we can transpose that gradient matrix and swap J and I. And what we're trying to do here is we're trying to express this in terms of a matrix multiply. So now that we've swapped the J and I, now the sum is over the inner dimension. That's what we want for a matrix multiply. So that's what we have here. So this is a matrix multiply between the first matrix and the second matrix, W minus W naught. But we're now looking at as you can see, the jth row and the jth column. So we have all these diagonal terms of this matrix, and we're summing across the diagonal. And you might remember that that is the trace. The trace is just the sum of the diagonal terms of this. And so far, we've kept the big O terms there, but at some point now, we're going to drop the big O terms, and we get an approximation. And that approximation is going to be good as long as W is close to W naught. And now, this trace ends up being the inner product for matrices, or at least real valued matrices. So if you have two matrices, A and B, and you want to know what is their inner product, two ways to think about it. Either do the trace of one transpose times the other. Maybe a slightly easier way to think about it is you just do an element-wise multiply of those two, and you sum over all the terms. So those are different ways to think about the inner product of matrices. But after you've done that, now you can kind of see that no matter what we're talking about, we always have the same form. The true cost can be approximated as the cost of the reference plus the inner product between the gradient and the deviation from the reference, as long as we're close. So it's sort of like no matter what the dimensions are, vectors, matrices, scalars, even tensors, we have this expression always. So that's kind of cool. So this is always this, no matter what the size, the shape of the quantities we're dealing with. Okay, all right. Any questions? Yes?
So how do you choose the reference?
The reference is going to depend on what you're analyzing. So like when we were analyzing this, we were applying these ideas, we said, we're at a point, we're moving in some direction U from that point. So that point was the natural choice to be the reference.
In this example, we were trying to find the steep of the curve, right?
Yes. So we're sort of sitting at a point and saying, at that point, how steep is it, and which direction is the steepest?
Yeah. So to check that, we assume the vector u, right, with the magnitude epsilon naught and the direction u, right?
Yeah. So we said we can move in any direction, any possible direction, and we saw that eventually, if we take a very short step in the direction u, that the slope is basically equal to this term. And then we did a little bit more analysis, and we said, okay, this term here, the way to maximize this over u is to choose u in the same direction as the gradient. That maximizes the slope. And furthermore, if we do that, then we saw that the slope itself is the norm of the gradient. So that's kind of what we concluded. Those two things. Yeah, so that was just one application of this. So depending on how you're going to use the linear approximation, you want to choose a good choice for the reference, something that makes sense. Okay, great. So I think this is enough for today. We'll do a quick example and look at some code. But I'll see you guys on Wednesday for that.